Welcome to the today's session. Previous sessions we discussed about amplitude modulation, time domain representation of amplitude modulation. In this session we will discuss about frequency domain representation of amplitude modulation. As we know, the amplitude modulated equation, which is represented by S of t will equals to AC cos 2 pi fct multiplied with 1 plus ma cos 2 pi fmt. If you open the bracket, S of t will equals to AC cos 2 pi fct plus AC ma cos 2 pi fmt into cos 2 pi fct. So first of all, we will split the above equation into two terms by opening this bracket. This equation will be splitted into two terms. Then, if this is your time domain equation, S of t, now we need to represent this time domain equation into frequency domain equation. By taking Fourier transform on both sides, we can represent the above equation in frequency domain. So S of t is time domain. If we apply Fourier transform for S of t, then we can represent it as S of f. Then coming to the first term as AC cos 2 pi fct, Fourier transform of AC cos 2 pi fct is impulse signal. So we can write it as, it is 1 by 2 del omega minus omega c plus omega plus del of omega plus omega c. Instead of omega, we can write it here f minus fc plus del of f plus fc. Coming to second term, which is AC ma into cos 2 pi fct and cos 2 pi fmt. So it is nothing but cos A, cos B. So the formula for cos A, cos B is cos A minus B and cos A plus B, which is nothing but, if you apply Fourier transform for that particular equation for the term, then cos A plus B plus cos A minus B, we will return with in terms of exponentials. If we represent the above equation in terms of exponentials, then by taking Fourier transform, we can rewrite the Fourier transform of AC cos 2 pi fct into cos 2 pi fmt as AC ma by 2 m of f minus fc plus m of f plus fc. The figure here showing is the frequency spectrum of amplitude modulation. The first figure shows the frequency spectrum of message signal. Then the next figure B represents the frequency spectrum of modulated signal of amplitude modulation. By observing this Fourier transformed equation, that is frequency domain equation, you can observe it is consisting of impulse signal and input message signal. So here it is representing as impulse shift signal is shifting from f to f plus fc and f minus fc. So at fc and minus fc impulse signal we are representing here in this spectrum. Then the message signal is from f plus fc, means it is also band limited to fc plus omega. Omega times it is shifting. So here we are writing it as fc plus omega, and at the negative side fc minus omega. Coming to minus fc plus omega minus fc minus omega. So this frequency domain equation we can represent by using frequency domain graph, frequency spectrum, where we call it as. By this frequency spectrum, we can understand that the amplitude modulated signal consists of two sidebands where we call them as upper sideband and lower sideband, where the upper sideband is Fc plus omega, a lower sideband means Fc minus omega. This is frequency domain equation representation of AM, and this is the frequency spectrum representation of AM. Coming to the other term, that is modulation index. Modulation index refers to it is a measurement where we can tell how much modulation is occurred. It is also named as depth of modulation or degree of modulation. Coming to the formula of modulation index, A max minus A minimum divided by A max plus A minimum, where A max is maximum amplitude minus minimum amplitude divided by maximum amplitude plus minimum amplitude. This also can be represented as AM by AC. If we need percentage of modulation index, we need to multiply with 100. This modulation index, depending upon the value, again it is divided into three types like under modulation, critical modulation, over modulation. If MA is less than 1, it is called as under modulation. If MA is equal to 1, it is called as critical modulation. If MA greater than 1, it is known as over modulation. The graphs we are showing here in this slide, under modulation, critical modulation, and over modulation. This we can observe practically while doing our amplitude modulation experiment by using our generation circuit, which we discuss in our next sessions. Where if it is under modulation, the waveform looks like this, fish-like structure. Here AM is less than AC. By varying this amplitude values, message signal amplitude values or carrier signal amplitude values, you can observe clearly this under modulation, critical modulation, and over modulation. If it is critical modulation, you can observe here amplitude of message signal will equals to amplitude of carrier signal. Then if it is over modulation, amplitude of message signal will be greater than amplitude of carrier signal. It is like we'll be getting some distortion, we will call it as phase reversal. You know, this is the carrier signal and the peak amplitudes which we are joining is nothing but message signal, which will looks like message signal. Thank you for listening. In the next session, we will meet again.